Okay, I think this is going to be part 5 of the November 23 paper 2 for physics IGCSE students. Okay, so we've been through the previous parts in other videos, so if you look in the same playlist, you'll find the other parts of these exam solutions, and I purposely do them in short videos so students are encouraged to listen to the audio. I keep forgetting to tell you, so when I listen to the audio myself, I don't listen at the speed I'm talking at. I increase the speed to, for me, I can listen to it at double speed because I'm the one who's made it. So I would suggest you increase the speed at which I'm speaking to be able to go through them faster, because I think you'll be able to keep up quite well. Obviously, when you're talking through a question, you need to talk very clearly. So to speak into the video is important that I speak clearly and I speak slowly so my thoughts come out correctly. But when you're listening and the video is already made, I think you can speed up the rate at which you're listening to them. Okay, so thanks for your support. If you've liked and shared the video with your friends, that's really helpful. I'm looking to expand the service to students in other schools, and I've already got over 700 subscribers, so the aim is to get to at least 1,000 in the next month or so. Alright, so this question is on forces and motion. So it's from topic 1 of the syllabus, the fundamental topic to do with anything to do with motion, forces, and in this case, in Unit 2, they like to ask about momentum. Okay, so this question is about momentum and forces. Now remember, momentum is mass times velocity. Then they want you to know what is the principle of conservation of momentum. So whenever two objects interact, the total momentum before, the interaction, so it could be a collision, for example, is equal to the total momentum after. That's the underlying simple principle of the conservation of momentum. So momentum must be conserved in any situation where there's an interaction. And really, if you then go into A level, you have to then say, providing there are no external or other forces that you haven't considered. Okay, so if you just got, for example, so you only need to put this first bit in to get the mark, because it's only a 1-mark question. But if you're doing this for A level, you'd need to explain that we're looking at situations, for example, where the friction is removed. You'll see that the momentum before is equal to the momentum after, because obviously friction is another force, and it can make it difficult for you to apply the principle of momentum. Okay, so that's the underlying principle. So this is what they want you to do, and so they want to reduce other forces. So in the diagram, part B, it says the diagram shows an air track. Yes, so the air track is shown underneath, and how it can be used to investigate motion without friction. So we want to remove friction because we want to have a situation where we're trying to remove other external forces which complicate physics. So, and then it said air. How did the air track work? You push air in, yes, at one end, and it comes out through the air holes, and that allows the glider to glide more smoothly on a cushion of air. Okay, so this is representing like how a spacecraft, because in space we have no friction, is to represent a spacecraft. So in this case, the spacecraft engine, or the model for a spacecraft engine, is floating at rest. It means not moving sideways on a cushion of air. So it's stationary, and the cushion of air is balancing its weight. So it's kind of just sitting there and not grinding along the air track. So the air tracks are usually made of aluminium. Okay, so that's the scenario. It says, state the momentum of the spacecraft engine, yes, which is the thing that's on the glider, yes, when it is at rest. So they just want you to make sure you know when it is at rest, yeah, its momentum will be 0, yeah. Now remember, momentum is mass times velocity, which is kilograms times the units of velocity, which is kilograms meters per second, okay? So when it's at rest, it has 0 momentum, okay? Let's make sure that you know that O means 0. Part 2 then goes on to say the spacecraft engine ejects large number of xenon ions to the left. So out of this is representing it. Out of this engine comes xenon ions, okay? So it's like that's the way that it's producing a force. Now remember, this is to do with Newton's third law. If some gas is coming out at the back, the momentum of the gas particles is pushed to the left, so that's going to produce, by Newton's third law, an equal and opposite force in the forward direction for the spacecraft. And that's how rocket engines work. And it then says a mass of 2.6 times 10 to the minus 24 kilograms of xenon ions, yes, leaves the engine with a mean speed, yeah, so that you could say the velocity or the speed is on average around 26 kilometers per second. So we know the mass and we know the velocity, which is what we were looking at before when we talk about momentum. So if we know the mass and we know the velocity, we can calculate the momentum of these ejected xenon ions. Okay, so I told you that momentum is mass times velocity, and we normally use P for momentum. Okay, don't ask me why, we just do. Yeah, so P is mass times velocity, and P refers to, so you should really write momentum when you're doing it in the exam to be crystal clear. So once we then multiply the mass, which we've been given 10 to the minus 8, 2.6 times 10 to the minus 8 kilograms, multiplied by 26 kilometers per second, we're going to change the kilometers per second into meters per second, so that's 26,000, you'll get a momentum of 6.76 times 10 to the minus 4, what's the units? Kilograms meters per second, okay? So the units here, where I've given the answer to 3 significant figures, should be in kilograms meters per second. Now, the reason I haven't put it there is I'm just showing you that I've given my answer to 3 significant figures, yeah, here, and then I've rounded it up to 2 significant figures in the final answer, because the data provided in the question here, the data provided is all to 2 significant figures, okay? And here they put the units for you, so you don't need to remember the units, okay? So that's the first page of this question. It then goes on to say, state the magnitude and direction of the spacecraft engine's momentum after it emits these xenon ions, after they leave the engine. So the xenon ions are moving to the left. Well, then they're by Newton's third law, yes, this is what they want to see that you understand. The momentum to the right will be equal to the momentum to the left, because momentum must be conserved. Yeah, before you ejected the ions, the total momentum was 0, And then if the momentum to the left is considered to be, say, negative, then the spacecraft will move to the right. Its direction will be in the opposite direction, and that will be to the right. So if we count the right as positive, which is mathematically the convention, and the ion leaving the engines to the left are negative, then because one is positive and one is negative, if you add them together, the total momentum afterwards will also be zero. So momentum has been conserved in this situation in rocket power, where Newton's third law is what's happening, the explanation for it. It then says the ions exert a force of 2.6 millinewtons. Now remember, milli means 10 to the minus 3 or 1,000th. Yes, so don't get confused. That's one of the easiest way of losing marks, is not realizing that you need to change the milli into standard form or to move the decimal place 3 places back. So the ions exert a force on the spacecraft engine. Yeah, tiny little ions are producing a force. The spacecraft engine has a mass of 1.2 kilograms. We know force and we know the mass. Well, then we know Newton's second law. If you're just looking at one object, you can use Newton's second law, and the acceleration will then be the force divided by the mass. Yeah? The force divided by the mass, yeah, is given by Newton's second law. All right, so that's Newton's second law. Calculate the acceleration, it says. Well, that's how you do it. Make A the subject of the equation, and they want you to give your answer again to 2 significant figures, because the data provided is to 2 significant figures. Here's the data provided. Yeah, the force divided by the mass, and you get to 3 significant figures or more. It will be 2.16 recurring, or 2.17. Yes, I should have put to 3 significant figures. Now, what do we want to do in the answer? You'll see what I've done. I've given the answer to 2 significant figures. Okay, so that's how you get the using Newton's third law. The Newton's third law is when you've got 2 forces acting on 2 different objects. One was the gas, one was the spacecraft. And then Newton's second law is when you're just analyzing what happens to one of those objects, in this case the spacecraft itself. Okay, so you eject gas particles out the back, the spacecraft will move in the opposite direction. It will move forwards. Okay. Question hasn't finished yet. So part C says the engine is designed to accelerate a spacecraft through space. Yes? So that's the situation. The spacecraft carries a certain amount of fuel. Yeah, and the fuel, remember, is xenon ions. 0.75 kilograms of xenon ions. When the engine is used, 9.9 times 10 to the minus 8 kilograms of xenon ions leave, yeah, each second. So you know how much mass is losing per second? That'll be in kilograms per second. So you can see, once you know how much is being left, you can see how long that fuel would last. Okay, you got, because this is a tiny amount, 10 to the minus 8. And then so this, as it says, a student suggests that this small spacecraft engine would not be useful because its acceleration it produces is very small. And we did that. The acceleration from part B was 2.2 times 10 to the minus 3 meters per second squared. Okay, and that was for 2.6 times 10 to the minus 8 kilograms of ions. When that much ions were ejected, it produced this small acceleration. But your job is to evaluate the student's suggestion, and we'll look at the mark scheme after this. Okay, So how do you evaluate it? Well, it means you've got to work it out. Is he making sense? So, at the tiny rate of fuel consumption, yes, so I've added in the word tiny. At the tiny rate of fuel consumption, yes, that we're given in the question, it could accelerate for millions of seconds. Yes, well, you could work it out. So they want you to see if you can put values to it. So if it can accelerate for millions of seconds, let me say 2-mark question. So if it can accelerate for millions of seconds, even if the acceleration is small, as shown here, where I just circled it, it will reach a very high change in velocity. The velocity change will be equal to that small acceleration for a large amount of time. We're talking about millions of seconds. So I quickly calculated, my calculation, that you could reach 16 to 17 kilometers per second. Okay? Now for 2 marks, I think I will get the 2 marks with that level of my calculation. Now remember, to get these marks in the exam, you need to have depth, detail, and clarity in your working. Let's have a look at the mark scheme, because what they have is 6 marking points for these 2 marks. So they probably looked at alternatives that students were providing, and they saw that there are many ways of explaining this. Yeah? Oh dear, I'm on the pen mode. Okay, so we've done, here's the calculations that we did, and part C, here's the points that I wanted to go through with you. Let's carry on in green. So we're looking at part C. So you can get your 2 marks from any of these marking points. So idea that we have a tiny amount of fuel consumed per second. Yeah. And then any attempt of a calculation. So calculation of time to run out. So I said it will take millions of seconds. So I would get that. I would have got the first 2 points already. Yeah. Now, if you actually do the calculations, you can see that that's 7 million seconds. Yes. That's what they've worked it out. Okay. So this shows that what I said, that the idea that it can burn for millions of seconds. Yes. This can burn for millions of seconds, and the idea that although it's a low acceleration, yeah, for a long time, can give a high change in speed, which I think I covered all these points. Yeah. So the mass of the spacecraft will be larger, so the acceleration is even smaller. That would be another marking point which I did not refer to. Okay, so I hope that makes sense. Now I don't know if we've finished the question. Let's have a look. I think we have. That's the last part. Yeah, that's the 13th marks. We'll go back to it. Yeah, this is from the previous question. So I'll leave this on for a second. So if you wanted to, this was in the previous video. I didn't show this mark scheme because it seemed quite simple, the question before. So going back to the question that we just finished, there's the final part of it. And now you have done conservation of momentum. You have used your knowledge of Newton's laws, both Newton's third law, and by ejecting gas and then analyzing the motion of the spacecraft, you're then analyzing a single object, and that will then be, if the forces are balanced, be Newton's first law. If the forces are unbalanced, in other words, there is an acceleration, then there is a resultant force due to the Newton's third law. The spacecraft moves to the right, the gas particles move to the left, and that conservation of momentum will gain momentum to the right for the spaceship, and ejected ions will gain momentum to the left as a balance to the momentum conservation rule. So you now have done a complicated question on conservation of momentum, and paper 2 is a good preparation for those of you who want to do A-level physics. And this is the kind of analysis you need to be able to do under exam conditions for A-level as well. Okay, so if you found that useful, like it, share it, and subscribe as requested in all my previous videos. Thanks for watching, and see you in the next video. Bye for now.